what is the first randomized algorithm that comes to your mind? Probably the first ever randomized algorithm that you've seen in an algorithm design course. It's probably QuickSort, right? So how does QuickSort work? We have an array of n elements. So n elements. And we just choose one of these elements as our pivot. So let's say I choose some element, and the way that we choose this element is actually going to be the important part. And then I'm just going to go over this array and find all the elements that are smaller than my pivot and all the elements that are larger than my pivot. So I break this array into basically 3 parts, but you can also think of it as 2 parts. So this is the set of all the elements that were smaller than my pivot. This is the pivot itself. And this is the set of all the elements that were larger than the pivot. And then I just sort this one and this one recursively. Okay. So let's analyze the runtime of this algorithm. And let's say that I only care about the number of comparisons that I do, because I'm doing sorting and everything else is a constant times the number of comparisons. So I'm just counting the number of comparisons here. So let's say T of n is the number of comparisons that I would perform on an array of size n. Well, basically, I have to compare everything with the pivot. Right? So I start from the beginning of my array and I compare everything with my pivot. So that's n-1 comparisons. And okay, then I have 2 different parts here. So let's say that the size of this one is h1 of n, and the size of this one is h2 of n. So the number of elements here and the number of elements here. So my total runtime would be T of n, which is n-1 comparisons that I did to do this part. And then I have to recursively sort this part. So it would be T of h1 of n plus T of h2 of n. Right? Okay. Now, what's the worst possible thing that can happen? In the worst case, I might pick a really bad pivot and it might be the smallest element in my set, or it might be the largest element in my set. And if that happens, then either h1 or h2 would become 0. So my worst case is that I have something like this. T of n is just, I did n-1 comparisons, and then the size shrank by only 1. Okay, so this is the worst case of QuickSort. How would you solve this? What is the solution here? This is n squared, right? Because I can just expand this, right? This is n-1 plus n-2 plus t of n-2. And then I can continue expanding this, and it would just be n-1 plus n-2 all the way to 1. And that's n times n-1 divided by 2, which is actually it's theta n squared. Okay. So if I do QuickSort, my worst case is n squared. And that's something that you've probably seen in an undergraduate algorithms course. But another thing that you have probably heard, but I'm not very sure that you've seen a proof for, is that the average runtime is actually n log n. And you might have heard that in practice, QuickSort is actually working better than merge sort. So what do we mean when we say the average runtime of QuickSort is something? So what do we mean when we talk about the average runtime of any algorithm? Well, we are assuming that we have some sort of distribution over the inputs, right? So if I say the average runtime of QuickSort is n log n, I'm probably assuming that every possible sequence of input is equally likely. So if I have n elements, let's say that I'm always doing my QuickSort over the elements 1, 2 to n. Okay, so I can assume that every permutation is equally likely. So I'm choosing a permutation uniformly at random, and then using that permutation as the input to my QuickSort. And then I can talk about the expected runtime of my QuickSort, or the average runtime of my QuickSort. But that's not really what we want to do here. So we will also talk about expected runtime. But what we mean here, especially in this module, is going to be a bit different. So I don't want to have any randomness in my input. I want to have all the randomness in my algorithm. So I want to allow my algorithm to generate random numbers or to access some source of random numbers. Okay. So specifically here in QuickSort, I want to ask my algorithm to choose the pivot uniformly at random. Okay, so there is no randomness in my input. All the randomness is in my algorithm. And this is something that we will keep for the rest of this module. So whenever I'm talking about randomized algorithms, all the randomness is in my algorithm. Whenever I talk about expected runtime, I'm talking with respect to the randomness in the algorithm. The input is always the worst case. So we're always analyzing the worst possible inputs that we can get. Okay. But in this particular case, actually, it doesn't make much of a difference for QuickSort, because I can just take my input, and instead of choosing random pivots, I can just apply a random permutation on the input, right? And that's effectively the same. But generally, this would be different, and I want you to keep in mind that the randomness is in the output. Okay. So choosing this pivot, we have many different options. So one option is to just take the first element as your pivot. And as we saw, the worst case runtime of that is n squared. That's not great. Another option is to try to find the best possible pivot. So ideally, what I like to happen here is that I want each of these two parts to be roughly the same size. So I want to find the pivot so that H1 and H2 are almost the same. Because if I do that, then I can say T of n is what? I have the n-1 comparisons with the pivot anyway, but then each one of these two becomes half of n. So I can write something like this. And I'm not writing the floor, but you will also have a floor. And yeah, you might also have a -1 here. Anyway, so if I find the best possible pivot, then my recurrence would look like this. And of course, this is the same recurrence that you have in merge sort. So this runtime is actually order n log n. So finding the best pivot really helps. And we do have algorithms for finding the best pivot. But that looks like a lot of work. So what happens if I don't exactly have the best pivot? What happens if, let's say, the sizes of the two parts can differ, but I put some bound on how different they can be? So what happens if I can find the pivot so that H1 and H2, let's say they're at most, okay, let's say H1 is between 1/4 of n and 3/4 of n. Okay, so I'm not finding the best possible pivot here, but I'm saying I don't want any of the two parts to be too small. So I can have a situation where this one shrinks as much as 1/4 of n, and I can have a situation where it grows as far as 3/4. So here, the runtime would look something like this. It would be n-1 plus t of n/4 in the worst case plus t of 3n/4. And actually, if you just do some induction here, you can see, or you just plug it in, you can see that this is also n log n. So as long as my pivot is chosen in a reasonably good manner, as long as I have a pivot that doesn't really break these two parts very unevenly, as long as I have some constant that tells me what is the relationship between this part and that part. So if I can say this part is at most a constant times that part, then I can say that my runtime is n-log. Okay. So now here's the part where we go into randomness. So let's say that I choose my pivot randomly. What happens intuitively speaking? So if I choose my pivot randomly, I'm choosing each one of these n elements with the same probability 1 over n. Right? Now, some of those choices are catastrophic because they can cause a situation where I choose, for example, the smallest element. But how many of those choices are good enough? And by good enough, I mean that they give me this kind of inequality. So if you just look at it for a second, you'll see that at least half of my choices are going to be good enough, right? So at least half of my choices are going to break my array into parts that are 1/4 of the original size and 3/4, or they're going to give me an even better partition. So intuitively, it makes sense that I can just say, I choose these elements and pivot by them. And intuitively, I should do at most twice as much work as the case where I could find a pivot like this. So intuitively, I should be able to get a runtime, an expected runtime of n-log n. So this is very hand-wavy. We're going to make it more formal. But how can I do better? Well, another thing I can do is that I can choose the pivot, and then I can form these two parts, and then I can check this inequality. I can check whether each part is at most 3 times the size of the other part. And if this inequality held, then I'm happy. This is a good pivot. I'm going to use this one as my pivot. If not, I just choose another pivot. I don't recursively try to solve these ones. Okay. So now if I want to analyze my runtime, what I can say here is that, okay, so forget about this part, which is the number of comparisons that we're doing here. In any case, I'm going to break this array down into 2 arrays, one with size, and size of each array is at most 3 times the other one. So I'm going to have the same recurrence relation, except that the number of here, the number of comparisons that I'm doing for finding the right pivot is going to change. But how many comparisons am I going to do in expectation to find the right pivot? So here's the thing. I'm choosing a pivot, and it might not be a great one, right? And then that might, well, the only way that I can know that this pivot wasn't a good one is to just compare it with everyone and see how many elements are smaller and how many elements are larger, right? So if I choose a pivot and it's not a good one, I'm basically wasting n-1 comparisons. But this happens only with a probability of a half. So I can just continue doing this and choose more pivots until I find a pivot that breaks this down in a good way. So what is the total expected number of comparisons that I'm going to do before I find a good pivot? Yeah, so first I'm going to do n-1 comparisons. And then with a probability of a half, I already have a good pivot, so I don't have to do any more. But with another probability of a half, I'm going to do n-1 comparisons again. Then again, with a probability of a half, this is it. This is all I wanted. But with another probability of a half, I have to do another n-1 comparisons, and so on. Yeah, so I'm assuming that my elements are 1 to n. All of my elements are different. Okay, so I keep doing this, and you can figure out that this sum is at most 2 times n-1. So I can say that at every step, then the expected number of comparisons that I do is just twice this much. And then my array breaks into 2 parts. One part has n-4, the other part has 3 n-4. And that's the worst case. Okay. So this shows you that if you just keep changing the pivot, you will actually get an algorithm whose expected runtime is n log n. Okay. But what if I don't want to change the pivot? What if I just say I choose a pivot randomly and I go with it, even if it wasn't a great pivot? So I want to show that even in that case, the runtime is still going to be n log n. Okay, so yeah, let me erase this one, this one. Now, if I choose a pivot randomly, I can no longer analyze it like this, because this is not such a great recurrence relation. Well, I can kind of expand this recurrence relation for every possible pivot, right? So I can say with probability 1 over n, my pivot is the first element, and then this breaks into 0 and n minus 1. With probability 1 over n, my pivot is the second element, and then this is 2 and n minus 3, whatever. 1 and n minus 2, and so on. Okay, so I can do that, but that's quite hard to analyze. So how else would you analyze this thing? So here's the thing. Let's say that, again, my elements are exactly 1 to n. Okay. In practice, my elements can be any other elements as long as they're distinct. But I'm just going to identify them with 1 to n only in the analysis. And here's the thing. So I want to find the total number of comparisons. If I want to find the total number of comparisons, I can take any two elements and just check if I've ever compared these two elements with each other or not. So let's say that I say xij is a random variable, and it's 1 if I ever compare I and j. If I is compared with j. And it's 0 otherwise. Okay, so what do I want to find? I want to find the sum of all of these. So I want to find the sum of xij's. And of course, I want to find the expected value of this sum, right? Because I want to know how many comparisons I'm going to have on expectation in total. Okay, but one of the good things about, and this is like, well, actually, let me write it with 2 sigmas, maybe. It's easier to say I from 1 to n and sum from j from I plus 1 to n of xij. Okay, so if you remember your basic probability, we have something called linearity of expectation. So I can rewrite this and I can just bring the sigmas out. This is the sum over every I, the sum over every j that is greater than I of the expected value of xij. Okay. So now the only thing that I have to do is to find the bound on this expected value. But what is this expected value? This is just the probability that I compare the ith element with the jth element. Okay, so let's find that probability. What is the probability that I compare the ith element and the jth element? And again, I'm assuming my elements are 1 to n. Okay, so I'm literally asking about the probability of comparing I and j, and I don't know where they are initially. So I have no assumption on my input. Initially, I might be here and j might be here, right? Even though j is larger than I have no assumption on my input. Okay, so let's see what our algorithm does. Our algorithm starts by taking a pivot. Let's call that pivot P1 because it's the first pivot. So I take my pivot P1 and then I divide my set of other numbers into 2 different sets. the ones that are smaller than my first pivot and the ones that are larger. So I can say here I have all the elements that are smaller than P1, and here I have all the elements that are larger than P1. And in each of these places, I'm doing the same thing again recursively. So here I'm taking some other element, let's call it, for example, P2. I'm taking it as the pivot, and then I'm dividing the elements in two different parts. Now, if I just draw this whole thing, it will give me a binary search tree, right? Because every time I had a pivot and I had the elements that were smaller than it, and I put all of those elements to the left of my pivot. And I had elements that were larger than it. Let's call this one, for example, P3, and I put them to the right. Okay. So now I have a binary search tree. But, okay. What I want to figure out is whether I and J were actually compared against each other. Okay. So one way to find that out is to go in this binary search tree and find where I and J are located. Now, let's say I have I here, just as an example, and I have J here. Then would I ever compare I and J? No. Why? Because, well, I chose P1 as my pivot. I compared everything with P1. Then I went to the left subtree and J went to the right subtree. So then I never compare anything from the left subtree to anything with the right subtree. So if I have a situation like this, I will never compare I and J. Now, based on this, you can easily guess when we will compare them. I and J are compared if one of them is an ancestor of the other one, or if one of them appears in a subtree of the other one. Okay. So now I want to know what is the probability that I is in the subtree of J, or that J is in the subtree of I. That's going to be my Xij. Okay. So what should happen in order for I and J to go into different subtrees? So it might be that they were separated here at the first pivoting, or maybe they were separated at the second one or the third one. But anyway, at some point, we have to do a pivoting. And when we do this pivoting, I and J should go to different parts. So what do we know about this pivot? Yes, so we know that this pivot is between I and J. Okay. So if I just look at all the numbers, I plus 1, I plus 2, all the way to J, the time when I and J are separated from each other is the first time that we choose a pivot in between. Okay, because then I is smaller than the pivot and J is larger than the pivot. So the only way that I and J would be compared against each other is if the first element that chosen in this range to be a pivot is either I or J, right? But we're always choosing our pivots uniformly at random. So each one of these elements has the same probability of being the first one who is ever chosen to be a pivot in this range. Okay? So the probability that the first pivot that is chosen in this range from I to J is either I or J is going to be 2, because we have 2 elements, I and J, divided by the number of elements that we have here. So what is the number of elements? It's J minus I plus 1. Okay. Yes, so we're considering all the elements from I to J, including I and J themselves. So what I'm doing is that I'm saying just look at the QuickSort and just look at what happens to this particular segment. So this particular segment I might at some point choose pivots that are smaller than all of this segment, so they stay together. I might at some point choose pivots that are larger than this segment. Again, they stay together. So what I want to know is when is this particular segment broken? So I don't care about I-1 and J+1 and so on. I just take this segment and I say the first time that I choose a pivot inside this segment is going to become broken. And now when that happens, if the pivot that is chosen is something other than I and J, then I and J will never be compared with each other. But if the pivot that is chosen is either I or J, then of course they're going to be compared because everything is compared with the pivot. So the probability that I and J get compared at some point is at most this much. 2 divided by J minus I plus 1. Okay, so we can just plug it in here. So this is sum over every I from 1 to n minus 1 actually, and sum of every J from I plus 1 to n. Now, instead of this, I can just plug in that. So that's 2 divided by J minus I plus 1. Okay. Now it's just algebra. I have to figure out how I can bound this sum. Okay. So how would you do that? So let's fix some I, and let's see what happens here. It's like I have J minus I plus 1, right? Okay, so I can say that this is, I can take all the possible values of J minus I plus 1, right? So what are the possible values? It can be 2, 3, 4, all the way to n at most. So this is at most the sum of I from 1 to n minus 1. And then here I just say the sum of 2 over some k, where k is from 2 to n. This is less than that, right? So now this sum is the same for every I. So I can say this is at most 2 times n minus 1 times the sum of 1 over k, where k goes from 1, sorry, k goes from 2 to n. Okay. So now what is the sum of 1 over k? It's just log n, right? Because, well, you can think of the integral. You can just integrate 1 over k, and the integral is the ln function. So the discrete sum is some constant times the integral. And so this whole thing is going to be O n log n. Because I have 2n minus 1 here, and this is the log n part. Okay? So overall, the expected number of comparisons that I'm going to perform in my QuickSort, if I just choose my pivot randomly every time, is going to be n log n. Okay. Let me erase and then go to the next one. And by the way, you don't need to take notes because we will give you the videos of all of these lectures. Yeah. If I erase too fast, sorry about that. You can just watch them. Okay, nice. Now, the next problem that I want to talk about is also a very classical randomized algorithm. And this is the MinCut problem, or minimum cut. Okay, so the problem is as follows. Let's say that I have a graph, and let's say that this graph has vertex set V and edge set E. And let's say it's undirected. And to simplify the matters, let's say we don't have any weights. So, but I can have multi-edges. Okay, so I can have a case where I have a vertex U and a vertex V, and I have many edges going between them. Okay, but to make it a little bit simpler, let's say I don't have self loops. So I don't have an edge going from a vertex to itself. This is not allowed. So I give you a graph like this, and then a cut in the graph can be defined in many different ways, but usually it's defined as a set of edges so that if you remove these edges, the graph becomes disconnected. So you can assume that initially the graph was also connected. I'm just writing all the assumptions on my initial graph here. Okay, so I give you a connected graph. It can have multiple edges between two different vertices. But what I want you to do is that I want you to find the smallest possible set of edges that if I remove them, the graph becomes disconnected. Another way of looking at this is that we can say we want to partition the graph in two parts. So this is a familiar thing that we will see over and over again. So I want to put some of the vertices on the left side and the other vertices on the right side. And I want to minimize the number of edges that go from left to right. Okay, this is the same thing, because you can just assume that this is one or more of your connected components, and these are the rest of your connected components. And then you're just removing all the edges that go from left to right, so you're disconnecting the left part from the right part. Yeah, but no matter how you look at it, we want to find the minimum cut. So we want to remove the minimum number of edges, or we want to do this division so that we have the minimum number of edges going from left to right. Okay. Now, you've probably seen a lot of complicated algorithms for this, and those algorithms usually use network flow. But we're going to have a very simple randomized algorithm. And here's my randomized algorithm. I say, suppose that I have two vertices, U and V, and let's say that they're connected by an edge. Okay. So there are two cases. Either in my optimal solution, U and V are on the same side, or they're on two different sides. One is on the left, one is on the right. Let's say that I magically know that U and V are going to be on the same side. Okay. So if I know that U and V are going to be on the same side, then I can just contract the edge between U and V and turn them into a single vertex. Okay, and how does that contraction work? Well, suppose that U is connected to a bunch of other vertices, and V is also connected to a bunch of other vertices, then both U and V become the same vertex, but that same vertex is going to be connected to all of these. Sorry, that one. And then I remove U and I remove. Okay. And especially if there was a vertex that was previously connected to both of them, it's now connected twice to this new vertex. Okay. So this is how I can contract an edge. Now, here's what I'm going to do. I'm just going to pick a random edge and contract it. And I'm going to hope that the random edge that I contracted was not one of the edges that was going to be removed in the optimal solution. Okay, that's all. That's the algorithm. So every time I just pick a random edge and I contract it. What happens eventually? Eventually, I will have only two vertices. So I will have a case like this, and I will have a lot of edges between them. Right? And then when I get to only two vertices, I say, okay, this is my cut. So all the edges that go between them. Now, let's just think about what's happening here. So when I contract an edge, what happens to the optimal answer, to the minimum cut? So let's say that the edge that I contracted was not one of the edges of my minimum cut. Okay. And by the way, the minimum cut is not unique. So I'm just going to fix some minimum cuts. So let's say that I magically know some minimum cut. And let's say that I'm talking about that minimum cut. So let's say that there is a minimum cut C. And I don't know how to compute it, but I can mathematically talk about it, right? So let's say that I've just fixed a minimum cut C, even though I can't compute it. So when I take an edge and I contract it, there are two cases. Either that edge was in my MinCut C or it wasn't. If it wasn't in my MinCut C, then it means that both sides were, both vertices that were in that edge were on the same side of this cut. So I merged these two into one, but that doesn't change anything, right? So all the edges that used to go from the left side to the right side are already going from the left side to the right side. So nothing changes if I choose an edge that is not in my MinCut. But it's a disaster if I choose an edge that is in my MinCut, right? If I choose an edge like this, then I'm merging two vertices on the two different sides. And then afterwards, the size of my MinCut might become much larger than the optimal answer that I had. Okay, so when I'm doing this, when I'm just taking edges randomly and contracting them, I'm always hoping that the probability that the edge that I chose is in the MinCut is going to be small. Okay, so if that probability is small, then it's fine. I can risk it. I can take this random edge and contract it, and it will very likely not be in my MinCut. That's the whole idea of this algorithm. And so the overall algorithm is that I just take edges randomly and contract them until I have only two vertices. And then I say, this is my MinCut. And if I want to find some better algorithms, or if I want to find better bounds, if I want to say that I want the likelihood of finding a non-optimal cut to be reduced, I can just repeat this algorithm, right? So maybe when I did it once, it gave me a wrong answer. But maybe if I repeat it 100 times, it will eventually give me the smallest number. So it's a very hopeful algorithm. Generally, just do the simplest thing you can and hope for the best. But now let's analyze it and let's see what kind of probabilities we have here. So what is the probability that we do this correct? So let's just focus on the first edge that I contract. What is the probability that the first edge was part of the MinCut? Okay. So initially, I had a total of E edges, right? And how many of them were in my MinCut? Well, C of them were in my MinCut. So the very first edge is going to be a disaster, is going to be in my MinCut with this probability. But this is not a great bound because, so here's the thing, I have multi-edges, so I don't really have a bound on E. And yeah, so, and I don't really know anything about C either. So let's do something. Let's say that my MinCut has exactly K edges. Okay, so if my MinCut has K edges, then here instead of C, I can just write K. But can I find a bound on the number of total edges, on the total number of edges in all of my graph? You see, the only thing that I know is that my minimum cut has K edges. But I can look into some specific types of cuts. The simplest type of cut is to just take one vertex and put it on the left side and put everything else on the right side. Okay, so let's say I do it. So let's say I put one vertex on the left side and I put everything else on the right side. then the size of this cut would be the degree of this vertex, right? But I know that my smallest cut has k edges. So the degree of this vertex has to be at least k. And this works for every vertex. So the degree of every vertex has to be at least k. And if every vertex has degree at least k, then I have at least n times k divided by 2 edges, right? Because each edge counts in the degree of 2 vertices. So basically what I proved is that the number of edges is at least this much. It's at least n times k divided by 2. Okay. So now I can plug it in here. So n k, and instead of saying divided by 2, I can just put the 2 up there. And let's cancel out the case. Okay, so this is nice. This tells me that the first time that I pick some edge randomly and I contract it, the probability that I screw up, the probability that the edge that I chose was part of my MinCut is at most 2 over n. And this is a small probability, right? Especially if n is large. If I have a lot of vertices, this is a small probability. Okay. But this was the probability that the first edge makes a problem for us. But we're continuing this, right? We're continuing until we have only 2 edges. So how many contractions are we doing in total? So every contraction reduces the number of vertices by 1. I'm starting with n vertices. I'm ending with 2 vertices. So I'm doing n minus 2 contractions. Okay, so I know that the probability that the first contraction screws up is at most 2 over n. But now, let's say that the first contraction was fine. What is the probability that the second contraction creates a problem for me? So I did my first contraction, and I'm just assuming that everything was fine. Now I have a graph with n minus 1 vertices, right? What is the probability that I choose an edge that is part of my MinCut? Well, I can do the exact same argument that I did here, but instead of having n vertices, now I have n minus 1 vertices. So that probability is at most 2 over n minus 1. And I can continue this. Okay. So now, what is the probability that eventually something goes wrong? What is the probability that in all of the n minus 2 iterations, at some point, I contract an edge that was in my MinCuts? The probability that the edge that I took is inside my set C is 2 over n. So the probability that it's not in the set C is n minus 2 over n. Right? Now, for the second one, I can also say something similar. I can say the probability that this one is not in the same C, in the set C, is n minus 3 over n minus 1 at least. So now what is the probability that none of them are in the set C? Yeah, it's the intersection of these things. So what I want is the probability of the intersection of all the, not epsilon's i's, okay? And if I take that product, the product is what? It's the product for n minus I minus 2 over n minus I. And the I ranges from 0 and can go all the way to n minus 2, n minus 3. I'm really bad with algebra. Okay, so the first one is n minus 0. Yeah, this can go to n minus 3.
I think the
Okay.
the denominator just comes from minus 1.
Yes. So yeah, if I just expand this, what I have is n minus 2 divided by n times n minus 3 divided by n minus 1 times n minus 4 divided by n minus 2. And at this point, I can start canceling, right? Times n minus 5 divided by n minus 3. Then I can cancel these two, and so on. And everything gets canceled until at the end, I will have a 2 and a 1 on top, which don't get canceled. And I have an n and n minus 1 down here. So it would be 2 divided by n times n minus 1. Okay. And what was this? So each one of these, this was the probability that I am safe after removing the first element. Then I had the probability of being safe for the second edge that I contracted, and so on. So I'm just taking this, and this would be the probability that, well, it would be a bound on the probability that I'm safe overall. So if I just keep doing these things, the probability that I never contract an edge in my MinCut C is at least this much. Okay. But this is not a great probability now, is it? Because, well, it's basically, let's say, 2 over n squared, right? So I have a probability of at least 2 over n squared to not really mess up this MinCut. But that's a very small probability. But now we can use the same technique that I talked about. We can just repeat the same algorithm again and again. So each time that I run my algorithm, I have this much probability at least of finding the correct solution. So what happens if I just run my algorithm n squared divided by 2 times? Okay, so what would be the probability that I get the best solution there? So I have an algorithm, and every time that I'm running it, the probability that it gives me the best possible solution is at least 2 over n squared. And let's say I run my algorithm t times. So run it t times. Now, what is the probability that I never get the right answer? Or what is the probability that I get the right answer at least once? So in the first run, I get the right answer with probability 2 over n squared. So what is the probability that I don't get the right answer in the first run? It's 1 minus 2 over n squared. In the second run, again, the same thing happens. I get the right answer with probability 2 over n squared, and I don't get it with probability 1 minus 2 over n squared. So if I want the probability that over t runs, none of them give me the right answer, that would be 1 minus 2 over n squared, all of it to the power of t. Okay. So if I run my algorithm t times, I get this probability. Now, the t that I chose was the inverse of this. So the inverse of my probability. So I chose n squared divided by 2. And the reason I chose that t is because we have this really nice inequality, right? So if I take 1 minus 1 over x, and I raise it to the power of x. Do you remember this from calculus? Yes. This is at most 1 over e. So if I run it n squared divided by 2 times, the probability that I don't get the right answer in at least one of the runs is at most 1 over e. Okay. But now I have an algorithm with a runtime that is much larger, but it's still polynomial. And it gives me the right answer with probability 1/e. So I can make this probability as close to 0 as I like by just repeating the algorithm. Right? Is it wrong? I think. Oh, is okay, it doesn't matter. Yeah. It's the probability of a wrong answer. So the probability of a right answer is more than 1 minus this. Okay. Yeah, anyway, with some constant probability, you get the right answer. Right? And if you get the right answer with some constant probability, then you can just repeat your algorithm and you can make the probability of getting a right answer 10 to 1 based on the number of repetitions that you do. So in practice, our algorithm is very simple. It's just that I take an edge randomly every time and I contract it. And I do this until I have only 2 vertices. And then I say, this is my cut. And then I keep repeating this. For how many times? Let's say for n squared times. Or some constant time n squared. Based on how much guarantee you want to have, like what you want the probability to. Okay. Yeah, so again, yes, this was the probability that we don't find the right answer. So the probability that we do find the right answer is 1 minus 1/e. Okay, now I want to talk a little bit about some complexity classes that we have here. So I assume that you know what P and NP are. So let me erase this one. Okay. So you know what P is, right? So P is the set of problems, decision problems that can be solved by an algorithm or by a Turing machine in polynomial time. Okay. So when we talk about decision problems, we're usually talking about languages. So what we do is that we usually say that we have some alphabets, and that alphabet is sigma. And because we're computer scientists, it's usually just 0 and 1. Right? So we write everything in this alphabet. And then a string would just be a sequence of 0s and 1s. And we use sigma star to show the set of all strings. Okay, so sigma star is the set of all finite sequences of 0s and 1s. And now I can say a language is just a subset of sigma star. So a language is just some L that is a subset of sigma star. So any set of strings is called a language. And now I can talk about the decision problem corresponding to each language. And the decision problem is that suppose I have some language, I give you some string, you have to tell me whether this string is in the language or not. Okay. And basically all of the decision problems can be encoded like this. So let's say that I give you some graph and I ask you, does it have an independent set of a particular size? Right? I can write all of my input using 0s and 1s, and then my language would be the language of all the sequences of 0s and 1s that encode a graph that has that desired property. Okay? So any problem can be thought of as a language, basically. And then when we talk about a complexity class is just a set of languages. So when I talk about the complexity class P, P is just a set of languages. And officially, we say that a language L is in P if what? If there exists an algorithm, and when we say an algorithm, we basically mean a Turing machine. Right? If there exists an algorithm A such that, okay, what conditions do we want this algorithm to have? So this algorithm basically takes the string as input and it either accepts it or rejects it, because we're talking about decision problems. So I want this algorithm to accept exactly the set of strings that are in my language. So the first condition is that for every string x, for every x in sigma star, A accepts x, and I write that like this. I write A of x equals to 1, meaning that A outputs 1 given the input x, if and only if x is in there. Okay, so that's the first condition. And of course, the second condition is that A runs in polynomial time. But for that to be formalized, where did I put the eraser? Yeah, for that to be formalized, I have to say I don't only need an algorithm A, but I also need some polynomial P, right? And then I want to say that for any input, the time it takes for A to run on this input X is at most P of the length of the input. Okay. So officially, this is what the set P is. The set P is the set of all the languages that have an algorithm such that that algorithm decides the language, and also that algorithm runs in polynomial. So in simpler words, it's the set of all problems that can be solved in polynomial. Now, my question is, what happens if we want to define a counterpart of P for randomized algorithms? So what does it mean for a randomized algorithm to solve a problem, let's say, in polynomial time? Now, we saw two different randomized algorithms today. And one of them, the algorithm for QuickSort, had this property that it would always give you the right answer, right? It would always sort the sequence and give you a sorted solution at the end. But there was some randomness in the runtime. We didn't know how long it would take. So the runtime depended on the randomness of the algorithm. But in the second algorithm that we talked about, the MinCut algorithm, the runtime there wasn't really that much dependent on the randomness. So we were always doing n-2 contractions, right? But it didn't always produce the right answer. So the probability that it gives us the right answer was not 1. So you see, we can have randomness in whether the algorithm gives us the right answer or not, or we can have randomness in the runtime of the algorithm. And this means that when I take something like P and I want to define a randomized variant of this, I can do many different things. And so I'm going to just give you some of these examples, and then we'll talk about them more next session. So first of all, we have to find a way to model the randomness. How can I model the randomness? I can just say that the randomness comes from a sequence of coin flips, right? And if I want to model that, I can just say that my algorithm no longer just takes one input, it actually takes 2 inputs. So the first input is going to be my actual input, X, and the second input is the sequence of random bits. So whenever the algorithm wants a random bit, it will just read from this sequence. Okay? So now, basically, when I have A of X and Y, and this Y has some fixed length. And we just assume that if Y has length n, it comes magically from the set of all strings of length n, and it's sampled uniformly at random. Okay, so I'm assuming that there is some oracle outside of my algorithm that is giving the value of this Y, and this Y is always random, and it's always uniform. Okay, so based on this, I can define what the set RP is, and RP stands for randomized polynomial time. RP. Okay. Again, it's going to be very similar to there. So I say a language L is in RP. Of course, I want to say it's in RP if it has a particular type of algorithm, right? If there is an algorithm A such that, okay, so here's the part where it gets interesting. So let's say that I take some string X, and let's say that the string X, sorry, I take some string X, and let's say that the string X is in my language L. What I want to say is that I want to say if I run this algorithm on X, then with a large probability, it will tell me yes. It will tell me that with a good probability, it will tell me that yes, X is in the language L. So I will have that the probability of this thing being 1. I want to say it's at least a half. Now, but the probability doesn't make sense, right? So for the probability to make sense, I should go back to that idea of having 2 inputs. So instead of just having an input X, I also have an input Y. Okay, and Y is the sequence of my random bits. But I want to only have polynomially many random bits. So I want to say the language is in RP if there is an algorithm A, a polynomial P, such that now I want to assume that Y is a random string of bits of length P of X. And okay, this is a uniform map. Okay, so what I'm doing is that I'm saying consider all the sequences of zeros and ones that have this particular length, and suppose that I take one of them uniformly at random. And I give that to my algorithm and say, this is all the random numbers that you can use. And if I do that, then for every input X that is actually in my language, I want the probability that my algorithm accepts that, and this is the probability over all Y, to be at least a half. Okay? Now, what about the other side? Well, for every X, what happens if X is not in my language? Now, this is the part where I can get creative and I can give different definitions. But for RP, the definition is that this probability has to be 0. Okay, so this is how we extend the polynomial time algorithm to the randomized setting. We say that, oh, and of course, I should have polynomial runtime, right? So for every, and okay, let's just write it like that. Let's say that A runs in polynomial time. Okay, which means, of course, because it's now getting 2 inputs, it means polynomial time based on the lengths of both inputs. But generally, what I want is something like this. So I want to have an algorithm A, and this algorithm A can basically flip coins, can have random numbers, but it can have at most polynomially many bits of random numbers. Okay, and instead of letting the algorithm just flip the coins anytime it wants, I just flip the coins at first and give the algorithm the result of all the coin flips, and that's why. Okay, And then I say that for every X that should be accepted, for every X that is in my language, my algorithm figures it out with a good probability, with probability at least a half. And for every X that is not in the language, the algorithm would always say that it's not in the language. Okay? And it also runs in polynomial.